Okay, welcome to the afternoon session or the lecture 2. So this morning we talked about the multiple access for GNSS, and we also discussed a little bit the signal design related to the multiple access, and we identified that most of the GNSS, they use an FD CDMA multiple access, the MA is already multiple access in the name. So they use an FD CDMA approach, and GLONASS uses an CD FDMA approach. And we have discussed why this is the case. We have experienced some of the properties, so some interference robustness. Also, we have calculated the processing gain and the spreading factor. And we have defined correlation. We have seen how the receiver can separate the different satellites. And now we will dive more into the spread spectrum ranging and explore also more signal properties of rangings or signals for ranging. So yeah, we will first start with discussing time delay estimation. Then we go into the part on signal properties, and in the end I will show you some generic examples of signal design to discuss these properties. Yeah, so based on the discrete model that we defined in the previous lecture, we can assume now, or we just that x is a random variable, and the signal x is a representative or a representation of the random variable x, and we consider only the period 0 for this time. So we consider only one period. And when we do that, we can give the probability density function parameterized by the parameter tau, so the time delay, as given here in the center, which is a Gaussian normal distribution. And the likelihood function with respect to the parameter tau is given as L of x of tau, and this is equivalent to the PDF. And the difference between the likelihood function and the PDF is given here below. So we have the likelihood is a function of the parameter tau, which is to be estimated at a given realization of the random variable x. So the given realization of the random variable x is our received signal at this moment. And we will use this representation or realization of the random variable x to estimate tau, while the PDF is a function of the realization of the random variable x for a fixed value of the parameter tau. So these are the same things, the same formulation, but with different ways to look at the same thing, kind of, because you have for the likelihood you have a realization of the random variable, and you're looking for the parameter tau. And on the other hand, you have the PDF, which is kind of a rule how to generate realizations of the random variable x based for a given tau. So now what we are going to do is as we are interested in estimating tau, this is our case, so the likelihood fits more to what we want to do. We want to estimate the time delay. And now we can maximize the likelihood with respect to tau. We can also maximize the log likelihood because the logarithm is a monotonic function. This helps us to reformulate the problem now, because we can take here the natural logarithm, and the PDF or the likelihood from the previous slide, we can now write in with these three terms. And when we drop all the parts that are not dependent on tau, because this doesn't change anything, right? So we're maximizing now three terms, and two of them are not dependent on tau. We can drop the first two. And then we can expand the last term which is done here. So we have minus, here's the minus. We can drop also this factor here because it doesn't influence the maximization or the estimation result of tau, because if we maximize a function multiplied by 1/2 sigma n square, or we maximize the function, it's the same thing. And then we end up here with the minus the L2 norm square plus 2 times square root of p x transpose c of tau minus p, and then the second moment, the L2 norm square of the code sequence. And as we discussed before, this L2 norm, the square of the PR sequence, is approximately n. So this is also constant, and we can also forget about this. The first term is also not dependent on tau. We can also drop this, and we can also drop these factors here, 2 and sigma p, square root of p. I'm sorry, and we arrive at the final result, which is very simple and also expected. This is cross correlation function. Yeah. So we calculate cross correlation with respect to tau, and we look for which tau this cross correlation is maximum. So and then this tau is our maximum likelihood estimate for the time delay. We can also call this a cost function, j of tau, this cross correlation function, and we're maximizing now this j of tau. In practice, and this is now how you can implement this maximum likelihood estimator with respect to a iterative process, and this can result into what's called the delay locked loop. DLL. In practice, time delay estimation is performed using a DLL, applying a gradient ascent method. So we have here a step size mu, which is larger than 0 clearly, and where the kth iteration can be given as. And we have here the kth iteration of our estimation. We calculate the gradient of our cost function at the previous time instant k minus 1, multiply this with the step size, and we take the estimate from the previous time instant iteration k minus 1, and this will generate us a new estimate at time instant k, or iteration k. The derivative can be approximated, so the derivative of this cost function j can be approximated using the central difference quotient of length 2 pi. So we have this here. So this is an approximation of this gradient or derivative. We use here we evaluate the cost function at plus delta and at minus delta, and we take the difference and we divide by 2 delta, and we can also now include here the cross correlation function. So we have to calculate 2 cross correlation functions, evaluate these 2 values, and we can then iteratively estimate the time delay. And now we can move to a stochastic version of this feedback system. So considering successive periods of k, now what changed from here to here is that we are now considering different data. So here this was always the same data, and we're iterating on the same data. And we can also now move to a stochastic version of this feedback system, where we consider data at consecutive time instances and adapt the estimate of the time delay based on this data over time also. And this is the basic functionality of a DLL. If we now, without noise, if we consider that there's no noise, and assuming that the receiver uses signal match correlators as we did before, and the definition of what is called the tracking error epsilon, which is tau minus tau hat, the so-called discriminator S curve can be given here with S of epsilon, which is then the autocorrelation function, epsilon minus delta minus the autocorrelation function of C epsilon plus delta, and here we have this in the discrete form. And this is equivalent to the central difference quotient of the cost function, as we had before on the previous slide. And this here is illustrating how this works, because here we have the tracking error and we have the autocorrelation function. This can be, for example, approximated by a triangle. And what we can see here is if the estimate is too large with respect to tau, this will be negative. So epsilon will be negative here, and then the early minus late, which is, this is the early correlation and this is the late correlation, will be negative. And then we have to decrease the estimate, and then we move here, for example, when we end, so we would iterate here to the peak of the autocorrelation function, and at the end, we would end up with early minus late being 0, and then we have found the peak over time. And this is how the iteration works. I mean, this is a concave function, and we're trying to iteratively maximize a concave function. Yeah, we can also calculate a lower bound for the estimation, for the variance of the estimator. If the derivative of the log likelihood, the expectation is 0, and then the variance, so this means that there's no bias, and the variance of the time delay estimation error, sigma tau square of any unbiased estimator, can be given by this lower bound here. So we take the 1 over the minus the expectation of the second derivative of the log likelihood with respect to tau. This can be reformulated applying some Fourier transform theorems to this formulation, and in the end leads to this formulation, and this is very nice. This also includes that we assume that the cross-correlation or autocorrelation function is only dependent on the chip pulse shape, as we have shown before. And here we can notice now two things. There is the equivalent noise bandwidth of the generic estimator. We have here also the SNR. This can be seen as a signal-to-noise ratio, this first term here, right? So because we have, it's 1 over SNR quasi, and then there's a factor of 4 pi square. And then we have also this, this factor here, which is called the Gabor bandwidth, or second moment of the power spectral density. There's several names for that. And we can see that the variance of the estimation error gets smaller. First of all, when we increase the SNR, that's maybe expected. So the higher the power we have, or the higher the ratio between power of the signal to the power of the noise, if this is getting larger, we can estimate the parameter better. But on the other hand, we have also this term here, which is only dependent on the shape of the chip pulse shape, right? So we can influence with the signal design the accuracy of the estimation of this parameter. So the idea could be, let's design a signal that has a minimum lower bound, for example. So we can discuss this in the following. Yeah, so this, as I said already, this term is called second moment of the power spectrum, root mean square bandwidth, Gabor bandwidth. And if you apply now here the derivative theorem of the Fourier transform and the Wiener-Khinchin theorem, you can arrive here that you see that this is the second derivative with respect to the tracking error of the autocorrelation function at 0. This means the curvature at the peak of the autocorrelation function. So when the peak gets sharper, the better we can estimate our parameter. This is what we can see here, and this is related directly to this second moment of the power spectrum. And what we can also see is, or what we can derive here, is if the chip pulse shape is band limited, which all the signals are that we are receiving. I mean, if we want to digitize the signal has to be band limited either by a filter or by its nature, the signal has to be band limited. And afterwards, so if this chip pulse shape is band limited, we can calculate an upper bound for this. Yeah, this is a parabola multiplied with the power spectral density of the chip pulse shape, which is always positive. This term. So we can say that this here, if we take the border frequencies of the parabola and assume that it's constant over the bandwidth, this is the upper bound. So then this is b squared times the power spectrum density of the chip shape, because the chip pulse shape is normalized to 1. And then we can, and as this is 1, so we can reformulate this here in the middle by b squared times the integral from minus b to b of absolute value of p of f squared df. This is 1. So we end up with this term. So the Gabor bandwidth is upper bounded by b squared. This is nice to understand because we can say, hey, this Gabor bandwidth, the higher the bandwidth, the better we can estimate the time delay. This is can be a rule of thumb. And you can find this a lot in the literature, not only on GNSS, but also on radar systems. They talk about bandwidth and talk about time delay resolution or time delay estimation accuracy. So here you can see why this is the case. The higher the bandwidth of the signal in principle, the higher, the lower the error, the variance of the time delay estimation error. There's the ultimate, let's say the ultimate maximum Gabor bandwidth is if we distribute all the power of our chip pulse shapes in 2 Dirac pulses at the band edge. Yeah, this maximizes this second moment of the power spectrum. But in time domain, this is either the cosine or a sine chip pulse shape. This doesn't really make sense because the time concentration of this chip pulse shape is quasi not concentrated in time. It's like infinite over time. It doesn't really make sense technically or practically, but theoretically it's interesting to see what happens. This indicates that for higher Gabor bandwidth, we have less concentrated chip pulse shapes with less time concentration. So their energy is spread over a longer time support. This is an interesting property as well. So we had here on this page, interesting property, the sharper the peak of the autocorrelation function at tracking error 0, the better we can estimate the time delay. In general, for higher bandwidth, we can estimate the time delay better, and we have also seen that minimizing the Cramer-Rao lower bound and maximizing the Gabor bandwidth and also maximizing then the time concentration of the chip pulse shape, they're contradictive tasks. Yeah, you cannot get it all. So because you would like to have a chip pulse shape that is very much concentrated in time, and you would like to have a small bound, right? But this is not possible. You will have to make a trade-off here, and we can already see this from these two equations here. Yeah, so let's talk a little bit more about these signal properties that we already started. So yeah, the higher, I just mentioned that, the higher the Gabor bandwidth of the signal, the higher the synchronization accuracy, because the variance of the tracking error gets smaller. Gets smaller, and that's why the synchronization accuracy is higher. Then the second moment of the power spectrum of the signal with bandwidth b is upper bounded by b squared. We have seen this, and this causes, or consequently, the higher the available signal bandwidth, the higher the possible synchronization accuracy. We have also seen that the higher the signal bandwidth, the higher the processing gain. So in general, high signal bandwidth is good so far. But okay, it's costly, maybe not available, but in general it's good. Then, the higher the processing gain is desirable, so for large bandwidth, and also we have high synchronization accuracy, high interference robustness. We also saw that if we have a higher processing gain, and we also have low intra-system interference. On the furthermore, minimizing the Kramer-Rao bound and maximizing time concentration, we saw that is a contradictive task, because we can see here if the Kramer-Rao bound for time delay tends to 1 over 2b square, the lower time concentration becomes, so p is tending to sinus or cosinus. Yeah. So we will have to make a trade-off. We will have to make a trade-off and say, okay, we want a signal that has reasonable accuracy or can provide us reasonable time delay estimation performance, and is also not too much spread over time. This is what we have to achieve. Yeah, what is time concentration? We already talked about this. So here's a definition here. Alpha is our time concentration. So this means the energy of the pulse within the chip duration compared or divided by the total energy of the chip pulse shape. And here we have the bandwidth concentration or frequency concentration, beta. So we have the energy or power that is dependent, because we have here this normalization, then this is also power. The power of the chip pulse shape inside the bandwidth and the desired bandwidth and outside. In our case, we will only consider strictly band limited signals, so from -b to b. This, I think, from my opinion, is this makes sense, because in the receiver the signal will always be band limited. So after receiving and down conversion and quantization of the signal, this will be, and sampling, this is a band limited signal. So it makes sense to look at this, and this is the signal that we use then for time delay estimation. However, using the uncertainty principle of the Fourier transform, the chip pulse shape cannot be strictly band limited and thus absolutely concentrated in frequency and also concentrated in time. This is not possible. So this alpha here cannot be 1. So alpha is always smaller than 1. As we can also observe that the maximum of the absolute value of the side lobes of the autocorrelation function can be given by these values nu I. These are the peaks, the side peaks of the highest values of the side peaks of the autocorrelation function. And they are, we can, for example, set up an upper bound for them, kappa, and they will be between 0 and 1, because the global optimum or the global peak of the autocorrelation function is always equals to 1 if we have a normalized signal. And then these nu I denote the value of the side lobes besides the global maximum. And then we can state here that the higher the side lobes of the autocorrelation function, the higher the side lobes of the chip pulse shape. So if we have more side lobes in the chip pulse shape, also the autocorrelation function of it becomes, the side lobes become higher, and the lower the time concentration, because we have more power outside of the main lobe of the chip shape, and that's why, or chip pulse shape, and that's why the power or the energy is spread over a longer time interval. Yeah, the higher the side lobes of the autocorrelation function, the higher this kappa becomes, the less robust the estimation of the time delay, because we have now a cost function with high side peaks. So we have to introduce an estimator that is maybe more costly, more intelligent than the gradient ascent method that we just discussed before. But in most of the receivers today, this gradient ascent method or a delay lock loop is implemented. So and there's also already some variants to avoid side peaks. But we have to be careful about these side peaks of the autocorrelation, especially when the noise increases and the peak increases. So because we have, if we have high noise, we can end up on the wrong peak, and this with our iterative scheme, and this causes strong estimation error. Another interesting property to consider for signals is the interference or the multiple axis interference performance. And I will introduce here a model that's used by Viterbi and was also used in the IS-95 and the CDMA 2000 standards for communications, and is also frequently used for GNSS. However, there are more detailed models available now that calculate the interference much more, let's say, precisely, but this gives us an idea about it, and I just will introduce this model so that you can see there's a lot of assumptions and what are the assumptions that are behind this model. So we have my A, so intra-system and inter-system multiple axis interference, my R, can be considered as additional interference components with zero mean. In general, both my A and my R are dependent on propagation characteristics of the transmitted signal. We will see this on the next slide. We will consider that there's a capital U users, for example, visible GNSS satellites with U from 1 to capital U, and each one they have power PU causing intra-system interference. We also consider V users of another system, for example, visible satellites of a different GNSS with V equals 1 to capital V, and they have the power PV, and they're causing inter-system multiple axis interference. Yeah, the received signal of another system, different GNSS, in the same frequency band, we can call the power spectral density here phi R of F. The reference pseudo-random sequence generator is, in our assumption here, perfectly synchronized. So we have estimated the time delay perfectly, and then we can look at the output of correlation, how the interference is affecting our signal, and and the time delay of the desired signal is known. This is the consequence of it. And the receiver was able to perform down conversion matched filtering, which means that our model assumed in the GNSS receiver is again perfect. So we assume that the chip pulse shape is known as it was transmitted from the satellite. And then we can set up this model. So we have, in general, the signal to interference plus noise ratio is the power of the signal plus the power of the noise plus the power of the intra-system interference plus the power of the inter-system interference, PR. So, and now we can set up these different, we can calculate these different powers based on these assumptions from the previous slide. So the noise power can be calculated here as the cross power spectral density between the noise and the chip pulse shape. So the model used in the receiver is calculated, is correlated with the noise, and then we can do a translation into frequency domain. This is very briefly explained this, and we can end up with N0 divided by 2 TD as the noise power. The power for the intra-system interference, we can see that we end up with this formulation, though PA is the sum of all these users, all the other satellites that use the same signal as the satellite of interest we're looking at, and then we have this cross power spectral density here of the received and model signal, and that's why we have here this power to 4. And the power of the multiple axis interference, also the inter-system multiple axis interference, then is the cross power spectral density between PF absolute the chip pulse shape, sorry, and the power spectral density of the other signal from the other GNSS. And here you can clearly see, if you are spectrally separated, so the two systems, the signals are spectrally separated. So when this becomes very small, the integral over the product, the interference becomes small also between systems. So when the signals are spectrally separated in our FD CDMA approach, This is beneficial for the interference between systems. We cannot do anything about the interference between the satellites because today, at least, all the satellites that transmit the same signal. We could also introduce different chip pulse shapes maybe for different satellites, but then we are moving to an FD-CDMA approach, right? So this is what is today. So if we are using a direct sequence CDMA, we have the same waveform for all the satellites from our system that we are interested in, and we have then the cross power spectral density to the other signals of the other system. And we can now explain some of these formulas or equations. So the background noise is assumed as white noise with spectral density of N0. The variance due to the background noise can be considered as, so after correlation, can be considered as white noise density filtered by the transfer function of the receive filter, which is then based on our model. All U users are assumed to be independent and unsynchronized with the desired signal. It is assumed that their time delays are independently uniformly distributed and their phases are independently uniformly distributed from 0 to 2 pi. The effect of the user, for example, a GNSS satellite, on the matched filter output of the desired signal will be that of white noise passed through the tandem combination of two filters with the transfer function absolute value of P of F squared. And this is then how we can calculate or approximate the intra-system interference. And similar assumptions as before can be also taken for the inter-system multiple axis interference. Now this white noise is passing through the transmit filter of the satellite of the transmitter, and also on the receive end through the receive filter. Yeah, and if we introduce that here, we can calculate a change of the SNR from SNR with respect to the SINR, and we can include that here. And get a nice formula. How does the SNR changes with respect to this intra and inter-system interference? Interestingly is to think about, is there a chip shape that would minimize the intra-system interference? I mean, we know already how the chip shape would look like to minimize the inter-system interference. If we are spectrally separated completely, the inter-system interference is 0. But how can maybe we can find multiple axis interference, intra-system multiple axis interference optimized signal, right? And indeed, there is a lower bound for the intra-system interference, which can be given by that this integral here over the power spectral density of the chip shape squared is larger or equal than 1 over 2b, and is equal if and only if, this is not a typo here, if and only if this power spectral density of the chip shape is flat from minus b to b, and in time domain this is a sync pulse. This is also the pulse selected by the IS-95 standard. It's a communication standard of spread spectrum signals, because they have hundreds of users and they need to minimize the intra-system interference. This is the dominating problem they have. In our case, it's not dominating, but we can see how can we calculate this lower bound. So there exists a pulse shape which minimizes the intra-system interference. We can use here the Cauchy-Schwarz inequality, and then we plug in here for x1 power spectral density of the chip pulse shape, x2 is equal to 1. We also assume again that we are normalized, we normalize the power of the chip shape to 1, and thus it follows here that this integral to the power of, with the power of 4 here times 2b is larger than this, and this is 1, and we arrive here at the lower bound. So this is interesting. We can also consider a signal design that could minimize the intra-system interference and so optimize our performance. Yeah, and I said this already. Yes, these assumptions are all derived from the IS 95 and the CDMA 2000 standards, where the intra-system is the dominating source of error besides the noise. Then there in GNSS, there are different terms for this my A and my R. So they're called spectral separation. And especially the this term from my R here is called self SSC, so the self spectral separation coefficient, and the spectral separation coefficient here is the cross power spectral density between the signal of interest and the signal from the other system. These are the terms that you can find in the GNSS literature for these terms or these names you can find there. And then my A and my R has to be considered in signal design, especially by the chip shape, or can be treated in the receiver. So what you can do is, I mean, we are calculating, or we are estimating all the parameters of all the received signals in the receiver, right? So we do this for all the satellites. We estimate time delay, phase, amplitude, Doppler. What we can do is we can use a current estimate of the other satellites and subtract this from the signal. And this is what's then called multi-user detection and mitigation. This is also done in communications for many years already to reduce the multiple access interference. And this could be also done in a GNSS receiver, introducing complexity. However, at the moment, we can see that the modernization of GPS, the evolution of Galileo, the further development of Beidou, they all introduce more signals with larger power, payloads with capability to transmit signals with more power. So in my opinion, we are moving from a noise-limited signal system. In the beginning, there was only GPS and GLONASS, and they were fully separated in different frequency bands. They were not interfering with each other. And now we are having GPS, Galileo, Beidou, GLONASS, all in the same bands, all ramping up the power, all ramping up the number of signals. So I think we are moving from a noise-limited system to a noise and interference-limited system. So in the future, maybe we need to consider more this multi-user detection and mitigation. There's a few papers that already treat this in this area, but they have used the standard schemes that you can find from communication, but they are optimized for bit error rates, usually not for parameter estimation. So I think there's a worthwhile task to further investigate this, especially because, yeah, as I said, I think we're moving towards more interference among the systems and the systems among themselves. Yeah? There might be also a strategy for one system to say, hey, we want to use only our system. We don't want to use the others. So what would be a good strategy? Would be to reduce your power, right? You reduce your power, you let the others increase the power, and you introduce multi-user detection on the receiver end. This would have the effect that the signals with a large power, you can estimate them really nicely, the parameters, and subtract them. So you have good estimates of the parameters of the other systems. You can subtract them from the signal, and then you can estimate the parameters of the signals of your system really good. And you don't need so much power for this. But okay, you shift the complexity from having more power on the satellite to the receiver. The receiver needs to work more to achieve this result. But maybe this is wise. If you look at launch costs, if you look at power on satellites, how much this costs, because this is ramping, or this is increasing the weight of the payload dramatically. You have to use larger solar panels and so on. So maybe this is also a good strategy for the future to think about this, if ramping up the power is the best strategy, if all other systems are doing the same thing. But yeah, it's just thinking out here, thinking aloud. So yeah, we have now this interference. We can also calculate a Kramer-Rao lower bound, including this interference. So we can call this CRLBI interference. And then this, we can take the Kramer-Rao lower bound and just multiply with the delta SNR that we calculated, and we get an interference considering lower bound also. Yeah, now I would like to discuss some signal designs, and these are designs of some signals. They're not available as GNSS signals, but to study, I created them to study the effects and the properties that we just discussed. Here are just the parameters that I used to generate them. So we use 3 example pulses. One pulse has a kappa of 0.1. The kappa was the height of the side lobes of the autocorrelation function. So in this case, it's 10% of the main peak, 50% of the main peak, and 70% of the main peak. We used a bandwidth of 1.023 megahertz. Time bandwidth product of BTC equals 1, which means that the chip duration is 1 over 1.023 megahertz. The power of the users that we consider for the intra-system interference is minus 154 dB watt for 11 users. The noise power is minus 204 dB watt per hertz. In the following, the C is the speed of light. For example, we assume that for the following examples, we assume that there's no other system interfering us at the moment. So we are alone in the band. And we will also calculate a multipath error envelope, which gives us a good idea about multipath performance of a certain signal. And it also gives us a measure to compare the multipath performance a little bit. And it calculates the bias that is created in a delay lock loop that has to consider multipath, because as we have seen, the estimator is only unbiased if there's only one signal arriving. It becomes a bias estimator when several copies of the signal arrive. So he's not optimum for this, definitely not optimum for this scenario. And in case, we have then additive components to the line of sight signal, and the reflected signal has a 60 dB below in power of the direct signal. So the signal to multipath ratio is 6 dB, and the envelope then, this is defined by the cases if the multipath signal is either in phase with 0, a relative phase to the line of sight signal, or pi, also out of phase. This is the constructive and the destructive superposition. And then dependent on the delay, it's not fully, but okay, these are the 2 phasings with respect to the line of sight signal. Yeah, and here we can see the 3 chip shapes that I selected or created here on the left-hand side. So we see that the side lobes get higher and higher because the kappa gets higher and higher. This is what we discussed. We have also, for higher kappa, we have less time concentration. We see that more power is shifted here outside of the interval from minus 0.5 to 0.5 divided by TC. And on the right-hand side, we see the power spectral density of these chip pulse shapes, and then also of these spread spectrum signals, if we assume that the spreading waveform is random. So then we can write here, we see that here in a solid line for kappa 0.1. Kappa 0.5 is here in the dashed curve. So we see more and more power gets shifted to the band edge, right? So the Kramer-Rao lower bound should get lower and lower because the Gabo bandwidth increases and increases. And we have seen this, and this is the contradictive task that we talked about. The lower the Kramer-Rao lower bound, the lower the time concentration becomes. We can directly see this here from these examples. And here we can see the autocorrelation function on the left-hand side. We can also see that for higher kappa, clearly the time concentration also of the autocorrelation function becomes less. We have higher side lobes. I mean, clearly this is given by the kappa. And on the right-hand side, how we can see the peak is getting sharper and sharper for higher copper. Yeah, this is what we could see from the relation Gabor bandwidth to the curvature of the peak that we calculated. So the higher the curvature of the peak, the higher the Gabor bandwidth, and this means the lower the variance. So we can estimate the time delay better and better for higher values of copper here. And we can see this right here. This is the Kramer-Rao lower bound in meters, because this is multiplied with the speed of light. This is the assumed propagation of the electromagnetic wave in vacuum, and we can see that we have here a 2-3 dB gain between kappa 0.1 and 0.7. So we have a significant gain in performance when we choose higher kappas, but is less robust. Yeah, we have the problem of having here side peaks. Remember, we have to calculate the absolute value of our autocorrelation function, of the cross-correlation function. So we have maybe less robustness, but the peak gets sharper and we have higher accuracy if we find the main peak. So we can see that. And we can also directly see here the multiple axis interference. So for higher kappa, we have higher multiple axis interference. It's interesting, so the delta SNR is also increasing, and I just plotted here on the right-hand side, this would be the lower bound. So this would be the sync pulse, so that we can see how far we are away from the lower bound. I didn't plot the lower bound in this graph here, which I could do for the future maybe, to show also how but it will be above here somewhere, the lower bound. So the sync pulse performance in ranging. Yeah, and then we can also have a look at this multipath error envelope that we discussed, but here we can see that for the small time delays, which are very realistic in many scenarios, we have not really a significant change. Only for larger time delays, which are more and more unlikely to happen with such large power, we have a change, and we can see that for higher kappa, we have higher errors for these large delays, but they're very large. Yeah? And in a realistic scenario, maybe with such high power, you cannot find this very often. Then we can also see here which is the approximation of the derivative of the autocorrelation function, the slope of the S, or the S curve here, and then the slope is here. And the slope of the S curve is related to the accuracy, as we could see, is the curvature then, because the S curve is the approximation of the derivative of the autocorrelation function, and then the slope of this curve in epsilon equals 0 is proportional to the curvature at the peak, right? So we can see that for here at 0, the slope gets steeper and steeper, so we have higher accuracy. Yeah, we can also see that let's say the stable region of this S curve grows for higher kappa. This is also interesting. Yeah, in the end, I would like to summarize the main properties that we discussed today. So, yeah, so maybe I resume here. So on the left-hand side, we see the autocorrelation function of the 3 examples, from kappa 0.1 to kappa 0.7, and on the right-hand side, the interference, including Kramer-Rao bound, so the intra-system interference. What we can see here is that the higher kappa, the curvature at the peak of the autocorrelation function gets sharper, the peak gets sharper. So the curvature gets higher, and immediately we can see that, because we remember that this is linked to the Gabor bandwidth, so the Gabor bandwidth is increasing, and thus the variance of our time delay estimate is decreasing, so we have a better time delay estimation performance for higher kappa values. Here below, I also plotted the multiple axis, the intra multiple axis interference values compared to the absolute lower bound, the sync pulse. And we can see that for higher kappa, this interference is growing, but not that really significant. The delta SNR is growing from 2.53 dB to 1.99 degree. To 3, sorry, to 3 degree, from 2.53 dB to 3 dB. So we have a higher interference also, and this is because the gap here between the two curves is smaller than without this interference. If you considered only the Kramer-Rao bound for the white noise, this gap would be bigger here between kappa 0.5 and 0.7. But as the interferences, intra-system interference is growing, this gap is smaller. And here you have the values from the absolute lower bound, the sync pulse, and it has a low, really low intra-system interference of 1.87 dB. But in the performance, it would be here above the kappa 0.7. So it would have a not so good time delay estimation performance, but a very low intra-system interference. Yeah, let's talk about the multipath error envelope. We can see this here on the left-hand side. So the upper part, starting here, this part is the in-phase error, and then this other one here is the out-of-phase error, and we expect errors then in between these two curves, the two solid curves, dashed curves, or dotted dashed curves. And we can see that for small errors, multipath errors, we have not really a difference. But for larger errors than 0.5 TC, for larger kappa, we are expecting higher errors here. But these large delays in multipath with such high power, we assume 6 dB signal to multipath ratio is rather unlikely in reality, or is not happening a lot. But okay, we can see here again for the kappa 0.5, but here between 0.5 and 1, we can see higher bias for the 0.1. So yeah, it's a difficult trade-off with respect to multipath. We can see here on the right-hand side the S curve. The S curve is the approximation of the derivative of the autocorrelation function, and then here the slope of the S curve in 0 would be then the approximation of the curvature at 0. And we can see that we have a steeper slope here, or higher slope, which means higher accuracy in ranging, and also the linear region of the S curve is increasing for higher kappa. So now in the end, I would like to summarize the signal properties that we talked about. First, the higher the Gabo bandwidth of the signal, the higher the synchronization accuracy that can be achieved in terms of the Kramer-Rao bound. We remember that the Gabo bandwidth is one of the factors. 1 over the Gabo bandwidth is one of the factors of the Kramer-Rao bound. So when this Gabo bandwidth increases, the variance decreases. Minimizing the Kramer-Rao bound for time delay and maximizing time concentration. We saw that these are contradictive tasks. The higher the processing gain, so in general, the larger the bandwidth, the higher synchronization accuracy, and the higher interference robustness. The lower the Kramer-Rao bound, the lower time concentration, and we saw that when the Kramer-Rao bound tends to 1 over b square, the lower the chip pulse shape tends to sinus or cosinus, which is quasi not at all time concentrated. The higher the side lobes of the autocorrelation function, the higher the side lobes of the chip shape, and the lower time concentration. We also have seen that because also the higher the side lobes of the autocorrelation function, the less robust the estimator becomes. and this means also the higher this kappa value becomes that we define. And in the end, multiple access interference, so intra and inter-system, have to be considered in the signal design, especially chip pulse shape design. As we discussed before, we can separate the chip pulse shape design from the sequence design. In general, we could combat both MIA and MIR also in the receiver using multi-user detection and mitigation, which is not done today in great extent in GNSS, but as I said, could be an important topic for future works, because in my opinion we are moving to a interference limited system instead while we started decades ago with noise limited systems. So thank you for your attention, and let me know in the comments or here in the room if you have questions. Yeah. So your question is, can we shape this here, right? So the question is, can we shape this here to have a better multipath performance?
No, my question is, if you increase the bandwidth of the system, then the channel properties will be different. You will go to a kind of frequency selective channel. Does that will have any problem in increasing bandwidth?
In our case, if the delay is larger than one symbol of the chip shape of the PR sequence, it's quasi uncorrelated. You see the error is very small here. So
the paths will be really weak and
larger delays. So when you go to a fast fading channel, it is not a real problem because of the correlation properties of the sequences, in my opinion. Yeah.
So I understand. That's why we use CDMA.
Yes.
Okay. Thanks.
Any more questions?
Do we have questions from the chat? Okay.
No.
Good.
No questions
then we
from
can go into the coffee
chat.
break.
Yeah.
Yeah. So yeah, then I wish all of you a nice evening or night wherever you are. And tomorrow at 9 again.
Tomorrow at 9.
We continue then with lecture 3 here in the room. We will then later continue with the lab.
Yeah.
So see you tomorrow.
Thanks, Felix. Thanks all. See you tomorrow.